All right, so we're going to do number 5 on the Thursday review problems. This is the problem that I think would be considered the hardest. In some ways, it's not because the vector part we do isn't that hard, and the unit analysis we do isn't necessarily that hard, but it's the fact that we have to do all of them in the same problem is why we consider this probably to be the hardest problem. So I've made up a silly little question here where Carlos finds himself out in the middle of the ocean for some reason, and he's all by himself. And he needs to swim to this little island, or he's going to perish because there's a big current that's pulling him south. And he needs to make sure he gets to that island. And then he'll wait out. Hopefully, a rescue ship will pass by. So here he is. He's going to be swimming. He swims a certain speed. You know, this is how fast he swims, 2.5 meters per second. And that's how fast he's going to swim in the problem. We talked about on that other example how we had the robot swimmer that just only goes a certain speed. So Carlos is going to swim 2.5. He can go any direction he wants. And I hope it's clear that if he goes directly west, which is where the island is, he's not going to get to the island because there's a current going south, and that's going to mess him up. But luckily, the current is a little weaker. It's only 1.5. So that means that as long as he swims in the right direction, the current will pull him downward towards the south, but his body will actually move directly west, as long as what we call the component of his velocity is just right. Okay? So generally with all these problems, the first thing we want to do as I run over to the smartboard here is just draw the vectors and make sure we get a sense for them. My problem is, though, is the 2.5. If I draw the 2.5 in some angle like that, and I'm not going to write meters per second just to keep it clear because my writing's so horrible. If I add that in there, you don't know what it says. But if we look at this 2.5, as I group that so I can spin it, we don't know, really what angle he should go. We know that this is wrong. If he goes straight that way, the current's going to pull him down. So we have a guess that it's something like that. So I'm just going to go ahead and leave it like that. The other thing we know is the current. And since the current, which we know is south at 1.5 there, since we know the current is south at 1.5, we know that his velocity, and I could draw it, I guess, 1.5, we know that his velocity has to exactly cancel that. So we can figure out that the component of his 2.5, which is this guy right there, has to be 1.5. Okay? And that's nice because then when we realize that both of those things are happening, they're going to cancel. They're going to disappear. And the only thing that's going to happen is him going west. So that's really, really been the problem, is this south at 1.5 needing to get canceled. Okay? So his 2.5 that he's doing has to cancel the 1.5. Okay? So does that help us answer the question? I don't know. Let's take a look. If the 2.5 that we have is really going at an angle, then it's going both north and west. Okay? And so what that means is that as we go north, we're also going west at the same time. And the beauty of the components is that it tells us that. And so what I need you guys to do right now is let's figure out what that number is. So go ahead and do that. 2 exactly? Sweet. So the reason for that is this is proportional to a 3, 4, 5 triangle, and so that turned out nicely. And so we can just do it in your head. If you can't do it in your head, obviously grab the Pythagorean theorem and help yourself do that. So that's great. So now we know how quickly he's going to be moving. He's going to be moving at 2 meters per second west. Even though he's swimming at 2.5, he's only going to actually move at 2 meters per second going to the west. The one in the hypotenuse doesn't really get us how quickly he actually moves towards the island. The question, though, asked for direction, right? So it was what direction should he go? And we don't have that yet. Anybody have an idea how we can get that direction? Yeah, exactly. Yeah, exactly. Do we know this angle somehow? Do you have any ideas for getting that angle? Okay, good. Now it is. You're right that it's a special triangle, but it's not actually the 30, 60, 90. You know, the 3, 4, 5 triangle is a special triangle, but the angle isn't the 30, 60, 90 one. So how are we going to get that angle? Any ideas? Beautiful. Okay, so we're going to go second tangent on the calculator. So that's the arctangent. What's that called? And then we do the 1.5 divided by the 2. And we get that 37 degrees. Okay? So he needs to go 37 degrees north of west, which will work out because then his component north cancels his component south. Perfect. He's going to go 2 meters per second west is what he's actually going to do. Okay, so that's the first part of the question. The second part of the question asks for how long it's going to take. So we got to be careful here in our unit analysis. We want to use this 2 meters per second that we have as a conversion factor. We do not want to use that as our starting point on our unit analysis. Okay, that's an easy mistake to make. Instead, we want to think about the distance that he has to go, right? And it's 120 yards, right? Which is pretty annoying because it's in yards, but that's why it's a unit analysis problem. Okay, so here we go. We'll start with the 120 yards, and we'll go from there. So 120 yards. How are we possibly going to know what that is? Well, what we can do is we grab our yellow sheet that you'll have on the test. You get the yellow sheet for the test, and you're going to look in the length section, and you're going to look around. You're going to try to find yards in there somewhere. If I give you a unit that's not in here, you'll be able to get it. I'm not seeing yards here. So I think, is it here? It's not there. So I think I'm going to have to use a piece of information I just happen to know. I'll make sure on the test that you'll have it available to you. If not, during the test, make sure you say, Mr. Miller, there's no yards here. And then I'll help you out with that. So it turns out that 1 yard, right, is 3 feet. Okay, so there's a conversion that we can use. And we use that because the yard canceled, which is nice. Now we're in feet. You notice that we want to use the 2 meters per second. And in order to use that, I'm going to have to be at meters. But the yellow sheet does have feet to meters. So we'll go ahead and use that one. It says that 1 foot, right, is 0.305 meters. And now we're going to use sort of the key step. I'll change colors for it. This is an important step. We can say that 2 meters is 1 second. And we know that because of this, right? The fact that that was 2 meters per second enabled us to make this very important conversion factor right here. This is the one that really got us over into time. So that's very powerful. Now, if it was in seconds, we could stop, but I think I asked for minutes. Did I not? Anyway, I'm going to go to minutes. So 60 seconds is 1 minute. And then we'll be done. What did I ask for? No, it says minutes here. Right? Yeah, it does say minutes there. So we're going to do we did a good job of going from seconds to minutes. Let's make sure everything canceled. My feet canceled feet, and I made sure that the meter canceled meter, and finally the seconds canceled seconds. So indeed, the last thing we have is minutes, which is what's being asked for. So we can set equals here and see what the answer is. Anybody get an answer? You don't like it? Well, let's just do it real quick together and find out. Yeah. 0.9? That's pretty fast. That doesn't. Let me just check that because it just means I picked some pretty unreasonable numbers here. Anyway, 120 times 3 times 0.305 divided by 2 and divided by 60. And I'm getting 1 minute essentially, 0.9 minutes. So that was pretty fast swimming for 120 yards.